Hello viewers, I hope all of you are fine. In our previous classes, we already discussed what is dipole, what is electric field at a point P due to dipole, and how we can investigate torque on a dipole in uniform electric field. Our today topic is also an extension of our previous topic about dipole. So let's discuss our today topic. Our today topic is basically the potential energy of dipole in uniform electric field. Now the question arises how we can investigate potential energy of dipole in uniform electric field. For that purpose, let's suppose a uniform electric field applied from left to right and a dipole is placed in this uniform electric field. The separation distance of this dipole is d and the dipole moment is from negative towards positive. Now you people see here that the force on this charge is in this direction and the force on this negative charge is in this direction. It means that the net force in this uniform electric field on this dipole becomes zero, which we already investigated on our previous lecture. Similarly, we already discussed in our previous lecture that the torque produced in this case as a result of rotation of this dipole is basically in clockwise direction, which we already investigated in our previous lecture. Now let's discuss how we can find potential energy of this dipole. For that purpose, we know that the work must be required in order to rotate this dipole in this uniform electric field, and we know that W is equal to Fd, but we must have to replace this Fd term by its angular counterpart, and we know that T is equal to r theta, or you can say that S is equal to r theta. So by replacing D by r theta, we know that Fr is equal to torque. So W is equal to T theta. Now this equation and this equation are equal, but the only difference is theta is the angular counterpart of this linear displacement and torque is the angular analog of this force. So this equation is more useful than this in this case because here is the rotational effect involved. Now let's suppose that this dipole rotates through small angle d theta, for which the small amount of work dw is required. So dw is equal to minus t d theta, and we also know that at start the angle is maximum, and then due to the rotational effect the torque tend to decrease this angle theta. So that's why we also included here the negative sign. Now by putting the limits theta I and theta I represent the initial position of this dipole and theta f represent the final position of this dipole as a result of small amount of work done. So that's why by integrating both sides and putting the limits and by solving this equation after integration, we know that sin theta is equal to cos theta, and by putting these limits cos theta f minus cos theta I, so this is our final equation. Now let's suppose our initial position of this dipole is equal to 90 degree. It means that initial angle which make by this dipole with applied electric field is 90 degree. We know that cos 90 is equal to 0. So only cos theta f term left. So cos theta f, or simply we can put it as a cos theta. Now this is our final relation for the work which must be required in order to rotate the dipole through an angle theta. Now this work is basically becomes equal to the potential energy stored in a dipole, because as a result of this work the energy is stored which is equal to the potential energy of dipole. Now we can represent this equation also in dot product form. So this equation W is equal to potential energy or is equal to minus P dot E. So this is our final equation, or you can say that this is our final equation, which is represented by equation number 1. Now let's discuss different cases for the potential energy of this dipole. Now in which case the potential energy of the dipole is maximum. The potential energy of dipole is maximum when the dipole is placed anti-parallel to the applied electric field. For example, the field is in this direction, then the dipole must be in this direction in order to maximize the energy of this dipole. So the maximum potential energy becomes in case of angle 180 degree, because cos 180 degree is equal to minus 1. So minus minus becomes plus, potential energy becomes maximum, which is equal to PE. So This is our maximum case of potential energy, but in this case torque will be 0 because we know that T is equal to Pe sine 180 degree, and sine 180 degree is equal to 0. So it means that when the dipole becomes parallel or anti-parallel to the applied electric field, then in both cases torque will be 0. Now in which case the potential energy will be minimum? That is the case when theta is equal to 0. So the potential energy becomes minimum when theta is equal to 0, because we know that cos 0 is equal to 1. So potential energy minimum becomes minus Pe. In this case energy will be minimum, and again torque will be 0 because T is equal to Pe sine 0, and sine 0 is equal to 0. It means that torque again 0. So that's why we already discussed that whenever the dipole is placed parallel or anti-parallel to the applied electric field, so in parallel case the potential energy is minimum and the torque will be 0, and in anti-parallel case the potential energy is maximum and torque is 0. So these are different cases, and this is basically the introductory topic about the potential energy of dipole. I hope you like this video, and if you like this video then please kindly subscribe this channel. Thanks for your time, and be in touch with us for our next videos. Thanks.